So leading us on our expedition today is Leonid Levitov, professor of physics at MIT. Leonid earned an MA in physics at the Moscow Technical Institute, his PhD at the Landau Institute in 1989, and joined the faculty at MIT in 1991. Among his many accomplishments, in 1993, he predicted that certain electrical pulses can be transmitted in a noise-free fashion. This effect was observed in 2013, so he's now had the good fortune to earn the highest honor in physics. He's had a particle named after him, the leviton, which has become the basis of electron optics. In the past 10 years, Leonid has made fundamental contributions to our understanding of the electronic properties of graphene, which is a 2D sheet of carbon in which atoms can move, and that's one of the focus of our workshops here. So with that, I look forward to hearing more about sunflowers, learning the answer to this question, and let's welcome Leonid Levitov.
All right, welcome everybody, and please join me in discussing the relations between mathematics and biology and physics, and maybe to get quickly into what we are going to discuss. Let me start with saying that probably humanity's earliest inquiry in mathematics was the observation of regular patterns in time, like day and night, and around us, like regular patterns of spirals that you see in plants. And we don't know how long back this observation goes, but was discussed, and many people were puzzled about it and tried to understand it. And I mean, just to make it clear, I mean, if you look at the aster, whatever that is, or pine cone, or cactus, you see that the spines in the cactus, or the scales in the pine cone, or flowers in here arranged in spirals, and all look very pretty, regular, and you may be wondering what makes it look this way. And then much later, as human knowledge progressed, people started counting. And when you count spirals, you discover something even more interesting than what you just see with the naked eye. And to get into that, we need to do some arithmetic and talk about Fibonacci numbers. So Fibonacci numbers are integers, obtained by the following very simple rule. The first one will be 1, and the next one will also be 1, and the third one will not be 1, it will be 1 plus 1, and that's 2. And then the fourth one will be 1 plus, sorry, get the real pointer, will be 1 plus 2, which makes 3. And then 2 plus 3 makes 5, and then 3 plus 5 makes 8, and 8 plus 5 makes 13, and then 21, 34, 55, 89, and so it goes, right? So that's how you construct Fibonacci numbers, and mathematicians would say that sequence that we defined, 1 plus 1, 2, 1 plus 2, 3, 2 plus 3, 5, 5 plus 8, 13, and so on. You can, in mathematical notation, you can, denote by saying that the third Fibonacci number is f3, fourth f4, nth fn, and then the rule by which the sequence is obtained is that you take the two preceding numbers and then add them up to obtain the next number. Right? Hope that's clear. And so that's the Fibonacci sequence, and it's going to play the major role in our story. Fibonacci, I mean, before getting to our story, Fibonacci was Italian mathematician from medieval time, and according to Wikipedia, most talented Western mathematician of the Middle Ages. And so he introduced the sequence, not because of biology, not because of plants, but for a different reason, but it's going to be most important for us today. And the reason for that is that the sequence describes spirals that are found in nature, in almost any kind of plant. The spirals are described by Fibonacci numbers. So it is correct to regard this Fibonacci sequence as a natural phenomenon, like seeing ripples on the water, or five-fold fingers on each of our hands. And that's the status that Fibonacci sequence has. And you can make a pictorial relation to spirals, and we'll do it better in a little bit, as follows. You can start with a square, take a square one by one, and then putting these two squares together makes 1 and 1 square, and then take a 2 by 2 square and then attach it to those 1 by 1 squares. That makes a 3 by 3 square, and then add 3 by 3 square to that, and then that makes 2 plus 3, 5, and then 5 times 5 square attached to that will make a bigger rectangle of the size being 8, and then 8 by 8 will make it an even bigger rectangle, and then you can keep going and then attaching squares to squares and bigger squares to smaller squares and even bigger squares to that. You get an arrangement of squares, and then that, if you trace the corners, it will make a pretty spiral. And then the amazing thing is that the spirals that you see in nature are pretty much described in the same way. And we're going to make it more precise, but that's kind of a bird's eye view of what's coming. Okay, and so maybe rather than giving a long introduction that I usually give for this topic, what I'm going to do today is make use of videos that a friend of mine emailed me some time ago with the subject V. Hart does Levitov. So V. Hart is a self-described mathematician, musician, and she is a very talented person making amazing videos on math and music, and she's also a very talented artist, as you will see. And so what I would like to do is to turn it on. Let me see if I can do that. Oh. No, it's okay. I think we had it.
Say your mean. Say or mean you're in math class and your teacher's talking about, well, who knows what your teacher's talking about.
No, I need to get to 1. Where's 1?
It says part 1 of 3.
It's part 1? Oh, yeah.
Probably a good time to start doodling, and you're feeling spirally today, so yeah. Oh, and because of overcrowding in your school, your math class is taking place in greenhouse number 3, plants. Anyway, you've decided there's 3 basic types of spirals. There's the kind where as you spiral out you keep the same distance, or you could start big but make it tighter and tighter as you go around, in which case the spiral ends. Or you could start tight but make the spiral bigger as you go out. The first kind is good if you really want to fill up a page with lines, or if you want to draw curled up snakes. You can start with a wonky shape to spiral around, but you've noticed that as you spiral out it gets rounder and rounder. Probably something to do with how the ratio between 2 different numbers approaches one as you repeatedly add the same number to both, but you can bring the wonk back by exaggerating the bumps and it gets all optical illusion-y. Anyway, you're not sure what the second kind of spiral is good for, but I guess it's a good way to draw snuggled up slug cats, which are a species you've invented just to keep this kind of spiral from feeling useless. This third spiral, however, is good for all sorts of things. You could draw a snail or a nautilus shell, an elephant with a curled up trunk, the horns of a sheep, a fern frond, a cochlea, and an inner ear diagram, an ear itself. Those other spirals can't help but be jealous of this clearly superior kind of spiral. Better draw more slug cats. Here's one way to draw a really perfect spiral. Start with one square and draw another next to it that is the same height. Make the next square fit next to both together, that is, each side is length 2. The next square has length 3. The entire outside shape will always be a rectangle. Keep spiraling around, adding bigger and bigger squares. This one has side length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and now 21. Once you do that, you can add a curve going through each square, arcing from one corner to the opposite corner. Resist the urge to zip quickly across the diagonal if you want a nice smooth spiral. Have you ever looked at the spirally pattern on a pine cone and thought, hey, sure are spirals on this pine cone? I don't know why there's pine cones in your greenhouse. Maybe the greenhouse is in a forest. Anyway, there's spirals, and there's not just one either. There's 1, 2, 3, 4, 5, 6, 7, 8 going this way, or you could look at the spirals going the other way, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Look familiar? 8 and 13 are both numbers in the Fibonacci series. That's the one where you start by adding 1 and 1 to get 2, then 1 and 2 to get 3, 2 and 3 to get 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on. Some people think that instead of starting with 1 plus 1, you should start with 0 and 1. 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, and it continues on the same way as starting with 1 and 1. Or I guess you could start with 1 plus 0, and that would work too. Or why not go back one more to -1, and so on. Anyway, if you're into the Fibonacci series, you probably have a bunch memorized. I mean, you've got to know 1, 1, 2, 3, 5. Finish off the single digits with 8, and ooh, 13, how spooky. And once you're memorizing double digits, you might as well know 21, 34, 55, 89, so that whenever someone turns a Fibonacci number, you can say, happy Fib birthday. And then, isn't it interesting that 144, 233, 377, but 610 breaks that pattern, so you'd better know that one too. And oh my goodness, 987 is a neat number, and well, you see how these things get out of hand. Anyway, 'tis the season for decorative scented pine cones, and if you're putting glitter glue spirals on your pine cones during math class, you might notice that the number of spirals are 5 and 8, or 3 and 5, or 3 and 5 again, 5 and 8. This one was 8 and 13, and one Fibonacci pine cone is one thing, but all of them? What is up with that? This pine cone has this wumpy, weird part. Maybe that messes it up. Let's count the top. 5 and 8. Now let's check out the bottom. 8 and 13. If you wanted to draw a mathematically realistic pine cone, you might start by drawing 5 spirals one way and 8 going the other. I'm going to mark out starting and ending points for my spirals first as a guide, and then draw the arms, 8 one way and 5 the other. Now I can fill in the little pine coney things. So there's Fibonacci numbers in pine cones, but are there Fibonacci numbers in other things that start with pine? Let's count the spirals on this thing. 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The leaves are hard to keep track of, but they're in spirals too, of Fibonacci numbers. What if we looked at these really tight spirals going almost straight up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. A Fibonacci number. Can we find a third spiral on this pine cone? Sure, go down like this. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. But that's only a couple examples. How about this thing I found on the side of the road? I don't know what it is. It probably starts with pine though. 5 and 8. Let's see how far the conspiracy goes. What else has spirals in it? This artichoke is 5 and 8. So does this artichoke-looking flower thing. And this cactus fruit does too. Here's an orange cauliflower with 5 and 8, and a green one with 5 and 8. I mean, 5 and 8. It's actually 5 and 8. Maybe plants just like these numbers though. Doesn't mean it has anything to do with Fibonacci, does it? So let's go for some higher numbers. We're gonna need some flowers. I think this is a flower. It's got 13 and 21. These daisies are hard to count, but they have 21 and 34. Now let's bring in the big guns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 17, 20, 24, 42, 53, 54, 55. I promise this is a random flower and I didn't pick it out specially to trick you into thinking there's Fibonacci numbers and things, but you should really count for yourself next time you see something spirally. There's even Fibonacci numbers in how the leaves are arranged on this stalk, or this one, or the Brussels sprouts on this stalk are a beautiful, delicious 3 and 5. Fibonacci is even in the arrangement of the petals on this rose, and sunflowers have shown Fibonacci numbers as high as 144. It seems pretty cosmic and wondrous, but the cool thing about the Fibonacci series and spiral is not that it's this big, complicated, mystical, magical supermath thing beyond the comprehension of our puny human minds that shows up mysteriously everywhere. We'll find that these numbers aren't weird at all. In fact, it would be weird if they weren't there. The cool thing about it is that these incredibly intricate patterns can result from utterly simple beginnings. Say or me and you're in math class and your teacher's talking about, well, who knows what your teacher's talking about. Probably a good time to start doodling, and you're feeling spirally today, so. Say or me and you're in math class and you're doodling flowery petally things. If you want something with lots of overlapping petals, you're probably following a loose sort of rule that goes something like this. Add new petals where there's gaps between old petals. You can try doing this precisely. Start with some number of petals, say 5, then add another layer in between. But the next layer you have to add 10, and the next has 20. The inconvenient part of this is that you have to finish a layer before everything is even. Ideally, you'd have a rule that just lets you add petals until you get bored. Now imagine you're a plant, and you want to grow in a way that spreads out your leaves to catch the most possible sunlight. Unfortunately, and I hope I'm not presuming too much in thinking that, as a plant, you're not very smart. You don't know how to add numbers to create a series, you don't know geometry and proportions, and can't draw spirals or rectangles or slug cats. But maybe you could follow one simple rule. Botanists have noticed that plants seem to be fairly consistent when it comes to the angle between one leaf and the next. So let's see what you could do with that. So you grow your first leaf, and if you didn't change angle at all, then the next leaf you grow would be directly above it. So that's no good because it blocks all the light or something. You could go 180 degrees to have the next leaf directly opposite, which seems ideal. Only once you go 180 again, the third leaf is right over the first. In fact, any fraction of a circle with a whole number as a base is going to have complete overlap after that number of turns, and unlike when you're doodling, as a plant, you're not smart enough to see you've gone all the way around and now should switch to adding things in between. If you try and postpone the overlap by making the fraction really small, you just get a ton of overlap in the beginning and waste all this space, which is completely disastrous. Or maybe other fractions are good, the kind that position leaves in a star-like pattern. It will be a while before it overlaps, and the leaves will be more evenly spaced in the meantime. But what if there were a fraction that never completely overlapped? For any rational fraction, eventually the star will close, but what if you used an irrational number, the kind of number that can't be expressed as a whole numbered ratio? What if you used the most irrational number? If you think it sounds weird to say one irrational number is more irrational than another, well, you might want to become a number theorist. If you're a number theorist, you might tell us that phi is the most irrational number, or you might say that's like saying of all the integers, 1 is the integeriest, or you might disagree completely, but anyway, phi. It's more than 1, but less than 2. More than 3 over 2, less than 5 over 3. Greater than 8 over 5, but 13 over 8 is too big. 21 over 13 is just a little too small, and 34 over 21 is even closer but too big, and so on. Each pair of adjacent Fibonacci numbers creates a ratio that gets closer and closer to phi as the numbers increase. Those are the same numbers on the sides of these squares. Now stop being a number theorist and start being a plant again. You put your first leaf somewhere, and the second leaf at an angle which is 1/5th of a circle, which, depending on whether you're going one way or the other, could be about 222.5 degrees or about 137.5. Great. Your second leaf is pretty far from the first, gets lots of space and sun, and now let's add the next one 1/5th of a circle away, and again, and again. You can see how new leaves tend to pop up in the spaces left between old leaves, but it never quite fills things evenly, so there's always room for one more leaf without having to do a whole new layer. It's very practical, and as a plant you probably like this. It would also be a good way to give lots of room to seed pods and petals and stuff. As a plant that follows this scheme, you'd be at an advantage. Where do spirals come in? Let's doodle a pinecone using this same method. By the way, you can make your own phi angulotron by dog-earing a corner of your notebook. If you folded it so the edge is on a line, you have 45 degrees plus 90, which is 135, pretty close to 137.5. If you're careful, you can slip in a couple more degrees, detach your angulotron, and you're good to go. Add each new pinecone thing a phi angle around, and make them a little farther out each time, which you can keep track of by marking the distance on your angulotron. Check it out! The spirals form by themselves, and if we count the number of arms, look, it's 5 and 8. If you're wondering why spirals would form, and why always with Fibonacci numbers, you could morph back into a number theorist or a geometer or something, but here's just a little bit of intuition. One simple way to doodle a flower is to start with a certain number of petals, say 5, and when you go back around, add the next layer close to the first, but bigger. Each layer adds 5 new petals, and the 5 arms spiral out. Looks pretty spirally to me. Now go back to phi. You put out 3 petals before you go back around, and if I make them really wide, the next lap adds 3 petals that overlap a bunch with the first, and so on. If I started with skinnier petals, though, the second time you go around it doesn't quite overlap so much, and it takes 8 petals before it goes around twice and they overlap enough for you to see the spirals. So this time I get 8 and 13. I mean, none of the spirals are actually physically there on any of these plants, it's just the plant bits are close enough that you can see the pattern. So all a plant needs to do to get awesome Fibonacci numbers of spirals is add new bits at 137.5 degree angles. The rest takes care of itself. That the Fibonacci series is in so many things really says less about those things and more about mathematics. I mean, that's what mathematics is all about. Simple rules, complex consequences. A process so easy that even a plant can do it, can turn into these amazing structures all around us. just like a few simple postulates can give us an incredibly powerful geometry. I mean, that's all assuming that a plant can do it, but measuring the angles between plant bits, you can see they obviously do it somehow. I mean, it's not like they have anglotrons, but plants have been around a long time and have had a lot of practice, so that probably explains everything. And thus, we always get spirals of 5 and 8 on this flower, 5 and 8 on this artichoke, 5 and 8 on this pine cone. Even this cauliflower has 1, 2, 3, 4, 5, 6, 7. Anyway, we always get 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4? It's easy to dismiss these as mutant anomalies, but just because they're different and unusual doesn't mean we should ignore them. 4, 7, 11? What could these numbers mean? Maybe things aren't as simple as I thought.
One more? Okay.
Say you're me and you're in math class and your teacher's talking about, well, who knows what your teacher's talking about. Probably a good time to start doodling, and you're feeling spirally today, so yeah. So say you're me and you're in math class and you're trying to ignore the teacher and doodle Fibonacci spirals while simultaneously trying to fend off the local greenery, only you become interested in something that the teacher says by accident, and so you draw too many squares to start with. So you cross them out, but cross out too many, and then the teacher gets back on track and the moment is over, so oh well, might as well try and just do the spiral from here. So you make a 3x3 square, and here's a 4x4, and then 7, and then 11. This works, as in you've got a spiral of squares. So you write down the numbers, 1, 3, 4, 7, 11, 18. It's kind of like the Fibonacci series, because 1 plus 3 is 4, 3 plus 4 is 7, and so on. Or maybe it starts at 2 plus 1, or negative 1 plus 2. Either way, it's a perfectly good series, and it's got another similarity with the Fibonacci series. The ratios of consecutive numbers also approach phi. Okay, so a lot of plants have Fibonacci numbers of spirals, but to understand how they do it, we can learn from the exceptions. This pine cone that has 7 spirals one way and 11 the other might be showing Lucas numbers, and since Fibonacci numbers and Lucas numbers are related, maybe that explains it. One theory was that plants get Fibonacci numbers by always growing new parts a fifth of a circle around. What angle would give Lucas numbers? In this pine cone, each new pine coney thing is about 100 degrees around from the last. We're going to need a Lucas angulotron. It's easy to get a 90-degree angulotron, and if I take a third of that, that's a ninth of 90, which is another 10 degrees. There. Now you can use it to get spiral patterns like what you see on the Lucas number plants. It's an easy way to grow Lucas spirals if plants have an internal angulotron. Thing is, 100 is pretty far from 137.5. If plants were somehow measuring angle, you'd think the anomalous ones would show angles close to a fifth of a circle, not jump all the way to 100. Maybe I'd believe different species use different angles, but 2 pine cones from the same tree, 2 spirals on the same cauliflower? And that's not the only exception. A lot of plants don't grow spirally at all, like this thing with leaves growing opposite from each other. And some plants have alternating leaves 180 degrees from each other, which is far from both phi and Lucas angles. And you could say that these don't count because they have a fundamentally different growth pattern and are in a different class of plant or something, but wouldn't it be even better if there were one simple reason for all of these things? These variations are a good clue that maybe these plants get this angle and Fibonacci numbers as a consequence of some other process, and not just because it mathematically optimizes sunlight exposure if the sun is right overhead, which it pretty much never is, and if the plants are perfectly facing straight up, which they aren't. So how do they do it? Well, we could try observing them. That'd be like science. If you zoom in on the tip of a plant, the growing part, there's this part called the meristem. That's where new plant bits form. The biggest plant bits were the first to form off the meristem, and the little ones around the center are newer. As the plants grow, they get pushed away from the meristem, but they all started there. The important part is that a science observer would see the plant bits pushing away not just from the meristem, but from each other. A couple physicists once tried this thing where they dropped drops of a magnetized liquid in a dish of oil. The drops repelled each other, kind of like plant bits do, and were attracted to the edge of the dish, just like how plant bits move away from the center. The first couple drops would head in opposite directions from each other, but then the third was repelled by both, but pushed farther by the more recent and closer drop. It and each new drop would set off at a phi angle relative to the drop before, and the drops ended up forming Fibonacci number spirals. So all a plant would need to do to get Fibonacci number spirals is figure out how to make the plant bits repel each other. We don't know all the details, but here's what we do know. There's a hormone that tells plant bits to grow. A plant bit might use up the hormone around it, but there's more further away, so it'll grow in that direction. That makes plant bits move out from the meristem after they form. Meanwhile, the meristem keeps forming new plant bits, and they're going to grow in places that aren't too crowded because that's where there's the most growth hormone. This leads them to move further out into the space left by the other outward moving plant bits, and once everything gets locked into a pattern, it's hard to get out of it because there's no way for this plant bit to wander off unless there were an empty space with a trail of plant hormone to lead it out of its spot. But if there were, all the nearer plant bits would use up the hormone and grow to fill it in the space. Mathematicians and programmers made their own simulations and found the same thing. The best way to fit new things in with the most space has them pop up at that angle, not because the plant knows about the angle, but because that's where the most hormone has built up. Once it gets started, it's a self-perpetuating cycle. All that these flower bits are doing is growing where there's the most room for them. The rest happens automatically. It's not weird that all these plants show Fibonacci numbers. It would be weird if they didn't. It had to be this way. The best thing about that theory is that it explains why Lucas pinecones would happen. If something goes a bit differently in the very beginning, the meristem will settle into a different but stable pattern of where there's the most room to add new plant bits, that is 100 degrees away. It even explains alternating leaf patterns. If the leaves are far enough apart, relative to how much growth hormone they like, that these leaves don't have any repelling force with each other, then all this leaf cares about is being farthest away from the two above and below it, which makes 180 degrees optimal. And when leaves grow in pairs that are opposite each other, the answer of where there's the most room for both of those leaves is at 90 degrees from the one below it. And if you look hard, you can discover even more unusual patterns. The dots on the neck of this whatever it is come in spirals of 14 and 22, which maybe is like double the Lucas numbers, and this pine cone has 6 and 10, double Fibonacci numbers. So how is a pineapple like a pine cone? What do daisies and Brussels sprouts have in common? It's not the numbers they show, it's how they grow. This pattern is not just useful, not just beautiful, it's inevitable. This is why science and mathematics are so much fun. You discover things that seem impossible to be true, and then get to figure out why it's impossible for them not to be. To get this far in our understanding of these things, it took the combined effort of mathematicians, physicists, botanists, and biochemists, and we've certainly learned a lot, but there's much more to be discovered. Maybe if you keep doodling in math class, you can help figure it out.
Okay. Yeah, no, it's great, and it's actually a much better introduction to my story than I would give myself. But okay, sorry, is this? Yeah. So just to summarize what she said, so when we have spirals and we count them right hand and left hand, and the right spirals and left hand are always Fibonacci numbers, and they're always consecutive in Fibonacci sequence. So you can have a pine cone 5-8 or 8-13, and if it's a big one, it will be 13-21. And for sunflower, it can be 35-54, 55, and so on. And the name for this in biology is phyllotaxis, and the name was introduced by Goethe, the German poet. He was interested in that phenomenon among many other, as well as many other people. Phyllo is leaf, and taxis is arrangement, so this means leaf arrangement, and phyllotaxis is the name. And there have been many scientists and thinkers and mathematicians interested in that, and they all developed this picture that you just saw in Vihart's video about spirals, about how to count them, about lattices, and about what I'm going to talk about next. And maybe just mention that that this is Kepler, this is Leonid, and this is Turing, the father of modern computer science, and that's the biologist who did Van Interson, whose work I'm going to talk about next. And so many people have been interested in that, and there have been even claims going as far as saying that explaining why Fibonacci sequence arises in spirals seen in plants is as important as explaining Balmer's series in atomic physics, and maybe it will take us as far as that took us in Niels Bohr's hands. I'm not sure that that's what we're going to see, but you know, just to put things in perspective. Anyway, so exceptions. I think exceptions that she mentioned are interesting and important. So this is what I read about a long time ago in some popular science book that, you know, biologists who were serious about it, they did statistics on pine cones, cones of some pine trees in Norway, and found that 95% were Fibonacci, and then 4% were from that exceptional sequence that starts with 1 plus 3, and then 3 plus 4 is 7, 4 plus 7 is 11, 11 plus 18, 29. And then, well, of course, there are always some that you cannot count. And so the amazing thing is that when you see something spirally, it's either Fibonacci, I should probably stay here, either Fibonacci or Lucas, and almost never anything else. It can be curved, defective, or something where you cannot count. So the regularity is kind of amazing. You never have any statistical deviation away from Fibonacci number. If you have a sunflower which is 144, you never find 145 or 143. So the regularity is kind of amazing and hints at some interesting things underneath, right? In contrast, if you take a man-made pine cone, like in that Swiss clock, and count spirals on that one, that's always wrong. You can take, I never seen any right one. So if you are in Switzerland and you want to embarrass a Swiss clockmaker, you can go to a Swiss clock shop and tell him that his clock is wrong. And the natural cones are always right. So that's the amazing thing. Good. So before we get to what I'm going to talk about, which is the origin of Fibonacci numbers, maybe let's see if there are any questions. Yeah.
At the very beginning, you said something about the number 5 and fingers.
Yeah.
Can you explain a little more how that is inevitable, and then the decimal system?
So yeah, good. Thank you. So different organisms show different kinds of numbers, and the spiral things and Fibonacci numbers is what you find in plants. In other organisms, you find different numbers and different symmetry. For example, all of us have mirror symmetry, right? And other animals too. And animals tend to have this, fixed number of fingers, and like we have 5, and many others too. And so that's a whole different story. But there is definitely a question about what defines symmetry for other organisms. And I'm not sure it is as well developed as this thing, but there is definitely a question out there. Yeah, more questions. Ask something. Okay, so the origin of Fibonacci numbers. So the story that I want to tell, is kind of speaking metaphorically. I can use this quote from Terry Pratchett and say that at the beginning it was nothing, and then it exploded, and that was about the creation of the universe by Big Bang. But basically, the story that you will see today will be somewhat similar. The idea is that there is some growth process that starts with nothing, and then as new elements of a plant are added one by one, or as they're growing and interacting with each other, then by this process it explodes, and also deterministically goes into a Fibonacci pattern, right? And so to develop these ideas, we need some mathematical models, and People understood it a long time ago, and botanists themselves, and then mathematicians, geometers, and crystallographers, all together, they were developing models that basically looked like taking a pine cone and then representing it mathematically as some kind of lattice wrapped on a cylinder. Or if you cut the cylinder and unfold it, then you get a periodic structure in the plane. And so that's the type of model that I like to work with, and it abstracts away the curvature part on the tip and at the bottom, simplifies the geometry a little bit, and then in these terms you can define everything we need to make progress, and that's I think this is a copy from a paper by Brevet brothers. Brevet brothers, the one crystallographer that physicists here know well about because of Brevet lattices, and his brother was a biologist, and they together developed these ideas. Then there are other kinds of spirally structures, like spirals and that you can draw in plane, and I'm going to suppress that for today, but it's also an interesting story and can be developed in a similar way. And I'm going to focus on these cylindrical lattices, and what I'm going to talk about in the next 5 minutes is due to that biologist Van Itterson who developed much of that geometry. And so what the question he asked, which will be a very important question for us, what happens if you take disks and pack them in a spiral on a cylinder? And we're going to talk about it in a second. But before we get to that, let's define some parameters. If you have a lattice on a cylinder, you can parameterize it rather than just specifying where each of the points is. You can parameterize everything that you see here by just two numbers. You can take one unit labeled 0, and then the next one in height labeled 1, and then take the height, the relative height of that relative to the other, and then 2 will be the same height relative to 1 as 1 relative to 0, because this is a periodic structure, and 3 relative to 2 will be at the same relative elevation as 2 relative to 1, 1 relative to 0. So you just need one number, the relative height, and another number is the angle by what angle you rotate to go from 0 to 1. And if you have these two angles, then that's your as physicists say, your parameter space or phase space. And every lattice on the cylinder you see, you can parameterize by these two numbers. Okay, and that's an important observation. But one can go further, and one can ask. Let's suppose we have a lattice. And let's count spirals. And what is the number of spirals, helices, in that lattice? And of course, mathematically you can construct a lattice with any number of spirals, any number of right-hand spirals, any number of left-hand spirals. Mathematically speaking, Fibonacci and non-Fibonacci numbers are not are kind of the same. Fibonacci numbers are not selected in any way. There's something else that's going on, and just building a lattice is not going to solve it, but it's going to help a lot. And so I want to talk about that. So what he thought about was take disks and pack them in a lattice like so. Yeah, and sort of, where are these closed packed lattices on that? No, that doesn't look good. Where are they on that phase space? So this axis is this relative height, and this axis is angle. And then the interesting thing is that if you take all the closed packed lattices, they form a tree. And the tree, so each point of a tree is a lattice, and the lattice is defined by angle and height. and then if you take closed packed lattices, they form this kind of tree, and it looks interesting, and clearly there is some structure behind it, and we can talk about it later. But just let's take it as a fact, which is what he did, that they form a tree. And then on this tree, the lattices that look like square lattices, looking like so, they're in the middle of these, somewhere in the middle of these arcs connecting different nodes with each other. And then the lattices that are closed packed hexagonal or triangular, they're at the nodes. So all closed packed lattices form a tree, and then this tree has this branching structure with triangular lattices occurring at the nodes, and then other lattices somewhere in between. And then the last thing to say is that you can count spirals, and counting spirals after lattices unwrapped on the plane just means counting rows. So, for example, in this one, there is 1, 2, 3 rows going this way, and 1 and 2 rows going the other way. So that one will be of type 2, 3, and then here it's 1, 2, and just 1. So that will be of type 1, 2, and so on. And you can do the same thing. You can do the same thing with squares. And so after you count spirals and fill up this diagram, it looks very pretty, and it clearly hints at some structure, but it doesn't yet explain why Fibonacci numbers are favored over non-Fibonacci, because in this diagram, Fibonacci and non-Fibonacci pairs occur roughly equally. You see Fibonacci pairs, also non-Fibonacci pairs. If you go further out here, you can see any pair you like, right? So what we learned so far is that cylindrical lattices, they're a useful model, and they describe mathematically, they help to understand the structure of a pine cone in very simple terms. They do not explain why Fibonacci numbers occur in a predominant way, because all pairs are possible. And so this is where physics should come in. So here, I mean, all the geometry is done, and we need to do some physics to understand the origin of Fibonacci numbers, and that's what's coming next. So what we want, I mean, if you want to rephrase it in these terms, what you want to understand is why different branchings are asymmetrical. So suppose there is some reason that if I follow that tree up to here, then here I am more likely to go, or maybe I'm guaranteed to go this way rather than that way. And if I'm here, I'm guaranteed to go this way and not that way. So something that cuts the branches of the trees, and then if that's so, then we can connect all Fibonacci numbers together and avoid getting into non-Fibonacci numbers, right? And so that's what physics allows us to do. Basically, what we are going to do is to play the following game. So suppose we assembled somehow that simple lattice, starting with what Vihart started talking about, some plant in which leaves are growing on opposite side of each other, one there, one here, and one there, and then one here again, and so forth. And then imagine that somehow there is, in the growth, there is some compression or some interaction between leaves such that they repel each other, or units, or whatever will become leaves, that they repel each other more and more strongly. And this is implemented very easily by saying that we have that cylindrical lattice, and then all the points on the lattice are repelling each other by some interaction, and we're trying to, what they're trying to do is when you have repulsion, they're trying to go to the lowest energy state, but it's not the lowest energy state as is, but lowest energy state under compression. And so you start with the structure, and then and then you squeeze it. And as you squeeze it, as we'll see in a moment, it will deform and will evolve in an interesting way. It will follow basically in a guaranteed way. It will follow that part of the tree that we constructed where Fibonacci numbers are, and will avoid all non-Fibonacci numbers. And if you do all the math, you find that on the tree you get paths that don't branch equally right and left, but have gaps. And because they have gaps, then after you get to the first pair of Fibonacci numbers, then you get to the second pair of Fibonacci numbers, and so it goes. So they will appear. Fibonacci numbers will appear from a completely deterministic process, and that can be shown to be robust, independent of the type of interaction you try, repulsion of any kind, and so that's a good basis to claim that there is some robust, purely mechanical, physical procedure that generates Fibonacci numbers, Fibonacci patterns during growth, and in fact, if you try to find out what happens at this meristem that Vihar talked about, indeed, there the units that later will become scales, spines, florets, whatever, they are generated one by one, and they form kind of one-dimensional structure, and then it grows, and it grows in a closed space. And when it grows in a closed space, it experiences stress. And under stress, it will deform, trying to get to a lowest energy state under the conditions of imposed by the growth, and that, and then it will develop in this sort of way, and fairly simple math shows that you get Fibonacci numbers deterministically, unless you make a mistake. So if at the first bifurcation, at the first branching point, you go the wrong way, if you go here rather than there, and then continue without any jumps all the way along this line, then that will give a Lucas series. If you make two mistakes, then you'll get some other generalized Fibonacci series, but that's never seen. The two sequences that we see are Fibonacci which is obtained by deforming it without any mistakes, and Lucas which is do one mistake and then deform and then deform. So it is a robust behavior that follows from a purely mechanical analysis of what happens from growth under stress in a soft lattice. And so that's kind of the idea. And then, it's easy to do calculation, but then actually people went further on, and they did experiment. To test it, they've done the following. They've taken washers with some magnets attached to them, and then using these washers with magnets, and the magnets repel each other because they're magnetic charges, they could build what they call a magnetic cactus, and then these washers, the separation between the washers can be controlled by squeezing it. And when you squeeze it, it evolves basically like that, like that diagram on the previous graph. You start with structures when all the washers are far apart, and they form a structure of that type. And then as you squeeze them, these guys start to repel each other more strongly than this repulsion, and then they twist. And after they twist more, right and left, and then right and left, and as they keep twisting, they generate Fibonacci structures one by one, with higher Fibonacci numbers, higher and higher one by one, and so that's the experiment that kind of realizes that mechanical idea, and shows that it's right. There are other experimental realizations, including the one that Vihar talked about with ferrofluid droplets, And so they have done, I mean, not because we suggested it, they had a similar idea at the same time, but there are experiments showing very clearly that there is a simple mechanical explanation for Fibonacci patterns, and I think now that is an accepted fact. So I think that's the end of the main part. I mean, let's see if there are any questions. Yeah.
Are there Fibonacci sequences in the genome, for example, or in other things other than the plant world?
Yeah, so I think plants are special, so I think Fibonacci, I mean, I heard about Fibonacci numbers and genomes, but when you try to read it, not very clear that it's unambiguous. So I'm not sure. Maybe so, but I saw a couple of papers on that, but there was no follow-up.
What about in music, the harmonic series, that each note that is played has a sequence of tones that occur from an octave to a perfect fifth?
Yeah.
Minor third.
Yeah. Okay. So a friend of mine a long time ago, when I was playing with us, he tried that. He made music based on Fibonacci tones and let me listen to it. I survived. Yeah. Yeah. Now one can do it. I mean, wasn't anything special.
Well, now that you know this, why are you continuing to study this particular phenomenon in plants? Where do
Okay.
you think it is leading you?
So that I'm not sure. I mean, maybe I should be clear about it, that I'm talking about it here not because I'm working on this thing now, but because I think it's a good, well, A, entertainment, of course, B, it's a good topic for our workshop, and our workshop is on super lattices, which are soft lattices and nanomaterials, and they're not like that, but they're also not very much different from that. And so I thought it will be useful to talk about this for the people in the workshop, because there may be some relation that we don't know about. So this is the main reason. Yeah. Okay. Can I indulge and have 5 minutes for enthusiasts? So I mean, you saw that there is a KLA tree structure. And then enthusiasts will know immediately that if there is a KLA tree structure, then it means that there is some hyperbolic geometry behind it, right? And you can discover that hyperbolic geometry very easily if you take these two parameters that were introduced, angle and height, and relabel them as x and y, as mathematicians often do, and then define a complex number x plus iy, and then you discover that this energy, then the energy that we introduced is invariant under mathematical transformation when you take that complex number and then complex number mapped to another complex number. These are symmetries of the energy. And that energy that we introduced in the phase space that we introduced, the phase space of all the lattices, will have that symmetry. And that's an exact property, and because it's an exact property, mathematicians know how to put it to good use. You can take symmetry and identify fundamental domains of that symmetry, and then study what happens in the individual fundamental domain, and then extend your knowledge to other fundamental domains using symmetry. And the symmetry is very rich, and the entire plane that we introduced, that was height and angle, after you factorize it by that symmetry, boils down to a fundamental domain which is of that triangle shape. And then if you look at the profile, energy, the contour plot of your energy in one of these fundamental domains, you see that each fundamental domain, each curvilinear triangle, I mean, enthusiasts will understand what it means, it looks like a valley between three mountain peaks. So there is a minimum, and then surrounding it there are three peaks, and then in the next adjacent valley, there is a similar structure, and then if you apply the symmetry, you'll get the same structure in the next valley, and so on. So so if you think about what this branching means, it means that you're walking in a landscape, in a strange mountain landscape where there are valleys surrounded by 3 peaks, and then when you go through a pass to the next valley, then it will look similar. There will be 3 peaks around you, and then there will be 2 passes through which you can go to the next valley, and then all that branching is about how to navigate in that landscape in the right way. And then the statement that I made about growth under stress helping is that every time you enter the next valley, you're biased because your lattice is being squeezed along the axis, and that makes the right and left choice, taking the right path and the left path, unequal, and you take the path that you're biased to take by stress, and then if you do that, and that's a zoom in on what happens in one domain. Ask me later if you want, but you can look very carefully in what happens in one domain, and indeed see that this bias allows you to distinguish between right and left and go one way and not the other way. And if it's exactly the right kind of bias, as you can prove, that leads to Fibonacci numbers. And so in this way, you can explain what's going on without a computer. You can just say that because of that modular symmetry, we know that in each of these domains, the same thing is going to happen again and again and again. And then once we went this way to a simplest Fibonacci domain, we're going to get to a higher order Fibonacci domain, higher order and higher order and higher order, and we'll never get out of that. There will be Fibonacci numbers generated one by one as you compress your structure. So summing up, the notion is that you can explain the origin of Fibonacci numbers by the simple physical notion that in the growth there is a mechanical process going on in which everyone interacts with everyone, but also there is an anisotropic stress or extension applied. What was Terry Pratchett name? Explosion. Yeah, an anisotropic explosion. And then in that anisotropic explosion, the principle, the outcome of that will be the Fibonacci structure. And other structures can also be explained, but to get there requires making a mistake. And Fibonacci numbers are those where you don't make a mistake. And it's a robust behavior, and therefore we believe that we know where Fibonacci numbers come from, and so that's the end of the story. Thank you. Yeah.
What happens if you build a model where there's 2 stressors rather than 1?
That's a great question. So how to build? What happens if a model is built with 2 stressors rather than 1? It's a great question. I don't know, but it is a great question. It is. I mean, the reason I don't know is that it's not easy to implement 2 stressors in that setup. Let me tell you what I was thinking. So there is a way to implement 2 stressors in a slightly different setup to build a more complex geometry. And actually, at this workshop, people were talking about complex geometries that may be suitable. Actually, you talked about something like that, using metal gates and then applying voltages on the gates to squeeze charges, and maybe that's a way to do it. But we haven't looked into that.
One other question. If you have a probabilistic model instead and you put a stress on it, does it also generate a Fibonacci result, or is that totally different?
Probabilistic?
Yeah.
No, probabilistic is going to generate maybe something that will look like Fibonacci on average, but there will be statistical deviations that we don't see. I mean, when I first read about it, I went out and started counting, and it's amazing that you never find any mistakes. So I mean, statistical means mistakes with some probability, and these things never make mistakes. Yeah. So I mean, you mean biological experiment as opposed to physical experiment? So people looked into what happens at the meristem. They tried to bisect meristem and then you know, I read some biology papers from a long time ago, and they tried to look what happens in meristem, but that was invasive because when you let it grow and you dissected it before, then not clear whether you haven't influenced what's happening later. So I'm not sure if anything better happens since. Yeah.
Is there something for us to be learned from this, maybe in architecture or any other kind of design? If this is the perfect sequence, are we mimicking it elsewhere that maybe I haven't thought of?
I'm sure we're mimicking it elsewhere. It is related to golden mean ratio, which is mimicked everywhere in architecture. If you try to draw this rectangle, which is most pleasant for the eye, the aspect ratio will be what Vihart talked about, 1.661, etc. And so consciously, unconsciously, it is used in architecture because we like things which are pleasing. And probably there are more examples, but that's what comes to mind. More questions? Okay, done. Thank you.